Okay, we are going to spend a little bit more time looking at some domain and range, okay? It's probably helpful, honestly, if you just graph these, okay? So here we go. We're going to graph this very first one and do 2 divided by x. And we'll just hit zoom 6 to make sure we're all in the same window. And you can kind of see that this is what it looks like. I'm actually going to switch this calculator so that it's a little easier to see. All right, hang on one second. 2 divided by x. Oops, I've got something on here. I don't think I have anything else. And let me turn my stat plots off. That's probably what I have on there. All right, sorry. Okay, here we go. So this is what it looks like. Okay, so hopefully you can tell for this one that your domain is going to be from negative, it's going to be everything but 0. Okay, so if you look, we're just going to write these in set note or in interval notation because I think most people find that that's a little bit easier. So I go from negative infinity until I get really close to 0, and then again from 0 until I get really close to positive infinity. And this is my domain. Okay, my range will be the same thing. The only y value that's not listed because I have a horizontal asymptote right here, the only y value that I don't have is also 0. So it will be exactly the same thing in this case for your domain and your range. Okay, so there's that one. Then we will go on to the next one, which is 2 over x minus 7. Okay, so we'll kind of think about that. And I want to think about this actually algebraically first. So I'm going to go back to this one. We know that we cannot have zeros in the denominator down here. So I know for sure that x cannot be 7. Okay, x can't be 7 because if it is, that makes my denominator be 0. So I want to see how that affects the graph. And sometimes it's hard to tell on our calculator. So we need to be really, really careful about that. Okay, so 2 divided by the quantity, x minus 7, hit graph, and it looks like this. Okay, it does give me a horizontal asymptote in this case at 7, so you can kind of see what's happening there. It does give me a horizontal asymptote at 7. And then, or not a horizontal asymptote, a vertical asymptote at 7. Okay, where x is 7, and that vertical asymptote will be right here that you can see, and I should have made that a dotted line, but that's my asymptote. Okay, so my line's getting really rare. My graph is approaching that line and never, ever, ever touching it. So my domain in this case would be from negative infinity until I get really close to 7, and then again from 7 to positive infinity, but it never hits exactly 7. Okay, your range, if you can tell by the graph, gets really, really close to 0. Okay, so the only line on my y-axis that it doesn't hit is this horizontal asymptote right there, which is 0. Okay, so it's going to be everything but 0. So I'm going to go from negative infinity to 0, 0 to positive infinity. Okay, so there's that one. This next one, 2 plus 2 over x. Again, if you think about it algebraically, you cannot have a 0 in the denominator for your domain. So I know for sure that my domain cannot be 0. So I go back, oops, sorry, wrong thing. I go back here, I put my equation in, and it was 2, I'm going to clear this up, 2 plus 2 over x. And let's see how this changes our graph, if it does at all. Okay, all that did was we knew we would have a vertical asymptote at 0, at x equals 0, because that's what x can't be. And then hopefully you can see when we added that 2 on there, it just moved the horizontal asymptote up to 2. Okay, so that's all that it did. So in this case, my domain is going to go from negative infinity to almost 0, and then 0 to positive infinity. And my range will go from negative infinity to almost 2, and then 2 to positive infinity. All right, and then our last one here. We know that when we do this, we have to have numbers again that are greater than or equal to 0. Okay, so I know that x squared minus 8x plus 12 better be greater than or equal to 0 because I can't put a 0 underneath the radical. Okay, so if I think about factoring this, x minus 2 and x minus 6 like that, then x minus 2 has to be greater than or equal to 0, and x minus 6 has to be greater than or equal to 0, which means x has to be greater than 2, and x has to be greater than or equal to 6. Well, those kind of contradict each other, so you probably have to have the most restriction on there that you can, which of course would be x has to be greater than or equal to 6. X greater than or equal to 2 does not fit that restriction. So x better be greater than or equal to 6, okay? So that comes out to be a whole number. Then, when you take the square root of a quantity, the smallest number you can take the square root of is 0. And the square root of 0 is 0. So the biggest output you're going to get will be 0. So I already know that my y values have to be greater than or equal to 0. I'm going to confirm all of this really quick on a graph. So I am going to put this into our calculators, and it was the square root of x squared minus 8x plus 12. X squared minus 8x plus 12. Okay, I'll go ahead and graph that. All right, somewhere I screwed up here algebraically. Oh, yeah, okay. You know what? I kind of screwed you up over here. Sorry. We know our magic numbers are 2 and 6, right? It has to do with doing this plus and minus factor thing. So we know our magic numbers are 2 and 6. Now let's look at the graph and let's see what has to happen over here. Okay, so when we look at the graph, sorry, I kind of messed you up. When we look at the graph, you can see that your x values have to be less than or equal to -2 or greater than or equal to 6, and that your y values will start right here at 0 and go up. Okay, so on that one, your domain goes from negative infinity until it's exactly 2, or 6 to and positive infinity. And then your range will go from 0 to infinity. Okay? All right, these we're just going to worry about the domain, and we're going to do them just algebraically, and we're not going to put them onto our calculators or do anything like that. Okay, so we do just a little bit of thinking here. Here, I know that this quantity right here cannot be 0. Okay, but if I were to solve this, pretending it was an equal sign in here, I would get x squared equals 4, which means that x can't be either positive or -2. Okay, here what I know is that 4x minus 3 has to be greater than or equal to 0 because I can't take the square root of a negative number. So I add 3, divide by 4, and x has to be greater than or equal to 3/4. Okay, so here's the deal. If x has to be greater than or equal to 3/4, and then this means that x can't be 2 and x can't be -2. Okay, this is probably my biggest restriction here, that I have to have numbers that are greater than or equal to 3/4. Well, -2 I'm not even going to worry about then because that's not greater than or equal to 3/4. But this I do have to worry about. I know that I have to have numbers that are greater than or equal to 3/4, but it can't be 2. Okay, so it's going to look something like this. your domain will be from 3/4 until really close to 2, because it can't be exactly 2, and then from 2 to infinity. Okay? So I don't know why I did a fuzzy line there, but a bracket. If you wanted to write it in set notation, you could write it in set notation, and it would be something like this. X is greater than or equal to 3/4, but X is not 2. Okay, so if you want to write it like that, you can do that too. All right, now we've got a little bit kind of trickier things. So here we go. This, I know that it can never be 0. Okay, it can't be 0. If you subtract 1, I get x squared equals -1. Well, here's the deal. It looks like there should be a restriction down here, but there is no number that I plug in for x, positive, negative, anything, and I square it, which results in -1. Even if you put a -1 in for x, -1 squared is +1. You can never square a negative and get a negative quantity. So this down here, actually, there's no restrictions on. You can put any number in for x. It doesn't really matter. When you square it, you're never going to get -1, which would make the denominator be 0. Okay? Up here, however, 9 minus x squared has to be greater than or equal to 0. So negative x squared has to be greater than or equal to -9. Divide by -1, x squared has to be less than or equal to 9, which means x, and this was where it gets a little tricky, and I screwed up on that last one. Okay? X actually has to be between -3 and 3. So your two magic numbers are 3 and -3. Okay? And what I want you to do is I want you to test numbers on either side of that. Okay, so if you try to put in a number bigger than 3, so here's if you think about this on a number line, I want you to test some numbers over here. Okay, so let's put in -4. If you put in -4, you have 9 minus -4 squared, or 9 minus 16, which gives you a negative number. That doesn't work. Okay, let's try some numbers in between -3 and 3. So let's put 0 in. 9 minus 0 squared is the square root of 9. That works, right? So this is a go in here. And then let's test a number that's bigger than 3. So let's test 4 again. 9 minus 4 squared would be 9 minus 16. -7, can't take the square root of -7. So test some numbers on either side of those is the easiest way to think about this. But in this case, I know that my domain has to be between -3 and 3. I have no restrictions in my denominator, so I don't need to worry about that. All right, then we want to talk about continuity really quick. Continuity basically means that you can make the graph without lifting up your pencil. So this graph right here, I can make without lifting up my pencil. It's continuous. This graph, if you can see, has a hole right here. Whenever you have those holes in there, they're called removable discontinuity. Okay, if you have holes in there. And then if you have non-removable discontinuity, that means you can't just like hole and go on. You have to actually lift up your pencil to get to the next thing. This is jump, obviously, and then this is infinite discontinuity. That's when you have asymptotes in there. Okay, so those are non-removable. So really quick, this is asking me which of the following figures shows functions that are discontinuous at x equals 2. That means you need to lift up your pencil at x equals 2. Well, this one right here, if I go up and hit the graph, clearly you have a hole right there at x equals 2. And so when you have a hole there, then you have discontinuity that you're going to be looking at. And this one has removable discontinuity because it has a hole. I think I spelled that wrong. Okay, this one is continuous. If I look at what's happening where my x value is 2 and it hits the graph, there's no hole right there. So it is continuous at x equals 2. All right, this one is asking us which one are discontinuous at x equals 0. Okay, so to do this, first of all, you can just plug in 0. Okay, if you try to plug in 0 into this function, you're going to have a 0 in the denominator, which we know cannot happen. So I know I have discontinuity. Same thing down here. If I plug 0 in here, I have 0 in the denominator, which I know cannot happen. And so I know there's going to be discontinuity. I just want to figure out what kind. And so I'm going to graph these, and it should help me figure out what kind of discontinuity I have. So the first one was at 5 minus x over x. So I will put that in here. Let's see, 5 minus x divided by x. Hit graph. Okay, I know it's going to be discontinuous at x equals 0. You can see that you have a vertical asymptote at x equals 0. That vertical asymptote is right here. When you have vertical asymptote, it is non-removable. And it is infinite. Okay, so it's non-removable, infinite discontinuity. That's what I would say. Non-removable, infinite. All right, and then the next one, x to the 4th plus x squared all over x squared. You could probably simplify that if you wanted to, actually, and you could factor out an x squared off the top, and then you would have x squared plus 1 over x squared. Okay, so let's look at this one, and then you can see that these x squareds cancel. Okay, so let's look at this and see how that affects the graph really quickly. So x to the 4th plus x squared. I'm going to put the original function in. X to the 4th plus x squared all over x squared. All right. Here we go. Okay, it's probably a little bit hard to tell on your graph. It does help that it's colored, but you can maybe see a tiny little hole in here if you happen to have a colored grapher. Okay, if you go to your table and you go to an x value of 0, you can see that you have an error there at the x value of 0. So I know I have a hole at 0, which I expect it to have a hole. Okay, I just didn't know if it would be an asymptote or a hole or what, but it is discontinuous at 0. It just has a hole in it, so it is removable discontinuity because it just has a hole. Okay. All right, and then we want to look at increasing and decreasing really quickly. Increasing and decreasing, you're really going to just look at what their slopes are. And if it has positive slope on an interval, then it is said to be increasing, and if it has negative slope, it is said to be decreasing. Okay, so increasing for positive slope, decreasing for negative slope, and constant is when the slope is 0. All right, so we will look at this function right here and say whether it is increasing, decreasing, whatever. Okay, so on this interval down here, your slope is 0, so it's constant, and we'll talk about domain and range in a minute. Okay, it's also constant up here. And then in this section, your slope is positive because you're moving up and to the right. So in that section of the graph, you would be increasing. Okay, we're going to do one more where we actually are going to put them in domain and range. Okay, this is a little bit trickier, but hopefully you can see on this section of the graph, as you move to the right, your pencil is moving up. So this section right here has positive slope because as I move to the right, I'm moving up. This section right here also has positive slope because as I move to the right, I'm moving up until I get right there. Okay, so I have positive slope, or I'm increasing. And we'll do interval notation. So down here, my x value is at negative infinity until I have an x value that's really close to negative 1. And then again, when I'm really close to negative 1, up until my x value right here is 0. Okay, so that's where I'm increasing. I have negative slope because I'm moving down and to the right in those two sections. So I have negative slope, which means I am decreasing when my x values go from 0, and I could really probably have a bracket up here. It doesn't really matter at this endpoint, I guess, if you have a bracket or a parentheses. On one of them, you're going to have a bracket, on the other, you'll have a parentheses technically, but I guess it doesn't really matter. Anyways, from 0 until I get really close to 1, and then again, when I get 1, to until my x values hit infinity. Okay, that's where it is increasing and decreasing. All right, and we made it.